It's really daunting to think about sending these artifacts out into the galaxy
Yes.
to possibly exist longer than Earth.
The artifact that Bill Kurth, my guest for this episode, is talking about are the two probes that roam the space outside our solar system, Voyager 1 and Voyager 2. And amazingly, they're still sending data to Earth, and some of them are audio. And together with Bill, we'll explore how they're made, what they tell us, and of course, what they actually sound like.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. MDS, we have ignition, we have a liftoff.
What you've just heard is the launch of one of the two Voyager probes, Voyager 1. It started its journey into space on the 5th of September 1977. Yes, 48 years ago. And just a few days after its twin, Voyager 2, was shot into orbit, the 20th of August. Yes, you heard that right. Voyager 2 was actually launched ahead of Voyager 1. On the other hand, Voyager 1 is the one that hit the interstellar space first in 2012, followed by Voyager 2 in 2018. And, as I said before, they're still going and indeed still sending data. Some of you may know that the probes carry a message, a gold-plated copper disc containing sounds and images from Earth. Kind of a time capsule, really. On the off chance that an alien civilization one day may pick it up and find out what our species here on the third rock from the sun has been up to. It's something that inspired some science fiction authors and movie makers. But what you may not know is that in addition to carrying sound records, the Voyager probes also record sound. And I came across that by accident some years ago, looking for some ambient background music, largely to block out noise while working in an open-plan office, as we all do it seems. I found the following on a popular streaming website, The Symphonies of the Planets, sporting the NASA logo, and it lays claim to being based on the sounds recorded by the Voyager probes. Of course, that intrigued me. Sound in space? Sound recordings from planets? How is this possible? And in search of an answer, I thought, why not contact the very people who were and still are involved in the Voyager space program, like Bill Kurth, who's a researcher at the University of Iowa in the US, and as you will hear, involved in the Voyager program since its early days. I must say that I was very fortunate indeed to grab a few moments of Bill's time earlier this year, and together we talked about the incredible and ongoing mission that is Voyager 1 and 2. For 48 years, Voyager has been exploring first our solar system and now, for a number of years actually, interstellar space, something no other probe has ever achieved. And with a light day away, the probes are still sending us data and sounds from places where no one has been before. And all with technology from half a century ago, which, needless to say, is very different to what we're used to today. So come and join me and Bill Kurth for a bit of a space exploration.
Well, my name is Bill Kurth. I'm a research scientist at the University of Iowa. I actually started working on Voyager as a graduate student here at Iowa. I think the first thing I did on Voyager was write a document that described the telemetry that would come back from the plasma wave science instrument, the PWS as we call it. And after that, I worked on testing the instrument, the hardware, and finally did calibrations of it before it was launched. I was fortunate enough to finish defending my PhD thesis literally a month before Voyager 1 got to Jupiter. And I asked if I could stick around to see what comes back, and I'm still doing that.
Here you are. Yeah. When did it actually reach Jupiter?
It was in March of 1979.
Mm.
And then Voyager 1 was later that same, or Voyager 2 was later that same year.
It's quite amazing because Voyager, of course, is still going. It's, way past Jupiter, of course.
Well, the Voyager project, it's amazing. It was originally conceived as something called the Grand Tour.
Mm.
The planetary alignment, if you launched in 1977, would allow a spacecraft to visit all four of the outer giant planets, Jupiter, Saturn, Uranus, and Neptune. But back in the early 1970s, when this mission was conceived, nobody could imagine building hardware that would last for 12 years, which is what it would take to get all four of those flybys accomplished. And so it was de-scoped to do just Jupiter and Saturn. It was called Mariner, Jupiter, and Saturn. And around the time of launch, they renamed it Voyager. Now, in spite of the fact that it was just meant to be Mariner, Jupiter, Saturn, the engineers agreed to make no decisions that would preclude it from going forward beyond Saturn. And in fact, that's what happened.
That was one of the questions that I had later on, actually, because it changed the mission. I mean, as you say, it started with Jupiter and Saturn, and then it changed the mission to Uranus and Neptune. And now, actually, it's beyond that as well, as we will probably talk about that a little bit later.
Right. The administrative side of this is that once the Saturn flybys were accomplished, then I don't know what the mechanism was back then. Currently, there's something called a senior review that looks at missions that have accomplished their prime mission and would like to go on and do more science. And so they have to propose, this is what we plan to do in the next mission extension. And so I don't think that mechanism was actually in place at the time, but the Voyager project said we've got a healthy spacecraft. We have all the tools we need to go on and do the Uranus and Neptune flybys with Voyager 2. So that was agreed on, and we accomplished those. And after the Neptune flyby, the mission argued that, well, now we should keep going. We still have two healthy spacecraft, and we can go all the way to the interstellar medium, although at the time we had no idea how far that was. And it was renamed the Voyager Interstellar Mission in about 1990.
And it now is in interstellar space, isn't it?
Yes.
And it was actually in the news recently. I mean, recently at the time of recording means end of May 2025, when I believe I read a snippet of an article where it said that the thrusters were repaired, something that people believed couldn't be repaired about 20 years ago, but suddenly it was repaired, and so they could reuse them as a backup system, I believe.
Yeah, well, we could speak for the whole hour about the issues with Voyager's thrusters. And actually, it's not just Voyager. There's a number of spacecraft. I know we went through this on Cassini. They basically get something like hardening of the arteries.
Yeah.
There are rubber bladders in the fuel tanks that are infused with some silicon. And they've determined that silicon can leach into the hydrazine fuel and goes out towards the thrusters. And a little bit of that silicon gets deposited on the inside of the tubes that feed the thrusters. And those are only like 1/10 of a millimeter thick. So basically, they're depositing quartz in those very fine tubes. And many of the thrusters on Voyager are getting clogged up by that. The ones that they revitalized just recently, they thought they had failed because of a system called a catalyst bed heater. This is basically a heater that heats some aluminum. The hydrazine interacts with that aluminum, and that causes it to ignite, and that's how we get the thrust out of the thrusters. And those heaters stopped working. Recently, they decided, well, there's no reason why we can't try to turn them back on again. And if they turn on, we can continue to use those thrusters. So that's what they did recently. They got those cat bed heaters to turn back on. And presumably, if we need to switch because the current thrusters they're using get too clogged up, they can swap over to those, and hopefully they'll work for quite some time.
Yeah, but you're right. We can talk hours over that, but
Yes.
we're not going to, because we're going to touch on a different subject. Because I came across Voyager, but apart from the fact that there's also a disc on it, sort of, giving a snapshot of human culture, etc. But I came across it in a very different way because I listened to something called the Symphony of Planets, which we can talk about in a little while, I believe. It's a recording that says it's sound recordings from Voyager. And that made me think, well, how is sound actually recorded on Voyager? And how do you get sound in the first place in space? Could you give us an idea of what it actually is that Voyager records and how that is converted into sound?
Okay, well, the easiest thing to think about to understand this is if you were sitting on Voyager and there was a speaker output from our receiver and you plugged headphones into the back of our receiver and listened to what it was detecting, that's exactly the mechanism. We have electric antennas on Voyager, not a microphone. But the electric antennas collect waves in space. And it turns out that this particular receiver has a bandwidth from about 50 hertz to 12 kilohertz. And if you're as old as I am, you can't quite hear up to 12 kilohertz. But young people certainly can. So this is the frequency range of this receiver is literally in the audio frequency range. The receiver picks up these signals. They go through an amplifier, and then they end up going into a very early version of an analog digital converter. These are very common now, but at the time they weren't. And one of our engineers actually designed a 4-bit system. And what that means is we have 16 different amplitude levels that can be encoded. Well, it does 28,800 samples per second.
Right.
And those 4-bit samples get sent to the spacecraft tape recorder. There's a lot of history behind this, but we basically use the same telemetry format that the camera uses. The camera has 800 lines of 800 pixels to make an image, and each of their pixels is 8 bits wide.
Right.
The signals that come out of the PWS instrument, we actually use 2 measurements per pixel. So we put 2 4-bit measurements and 1 8-bit image pixel. They can send that back to the Earth the same way they send back all those pictures that you've seen in the textbooks for years and years and years. And it makes it very convenient.
Because it's the same mechanism of transmission.
It's basically the same mechanism. And this part of our instrument was kind of a late addition. It was basically the only way we could get the data back from it. Well, we can talk later about all the trials and tribulations of getting those data back from 165 astronomical units, almost a light day away. And that's a story in itself.
That certainly is. Well, 4-bit to begin with is quite a short range nowadays. Some audio systems have 16 bits, some of them have 32 bits, which of course is a much wider range. But I think we can listen to some of it now.
Yes.
And we will. And I think there is the first sample that I believe we agreed to play back is actually from Jupiter. And it has a bit of a story because I think it's related to thunderstorms on Jupiter, isn't it?
Right. So Voyager 1 did its flyby of Jupiter in 1979. And at that point in time, well, we all are familiar with lightning on Earth and thunderstorms and so on. And people had detected whistling tones related to lightning on Earth as far back as World War I, actually. Opposing sides at a battlefront would use telephones basically to send commands out to the front lines.
Yeah.
And the enemy would basically lay a long wire on the ground, hoping that they could pick up the telephone calls so that they knew what the enemy was going to do next. I don't know if that actually worked, but one of the signals that they ended up finding was whistling tones. And if you've ever watched old World War II movies and the bombs come whistling in, boom. That whistling tone was what they heard on these long wire antennas, and they didn't know what it was. And I think it was about 1950 that a Frenchman, Owen Story, actually figured out what was going on. Basically, a lightning stroke emits a very broad spectrum of electromagnetic radiation from a few kilohertz up past the visual wavelengths and even beyond that. In the range of a few kilohertz up to maybe 10 kilohertz, when these radio waves propagate upward, they can get into the ionosphere of Earth, which is a charged plasma, and then they do something we call a mode coupling. They no longer propagate freely because in order to propagate through a plasma freely, the frequency has to be above what we call the plasma frequency that's dependent on the density of electrons in the plasma. Well, at Earth, that's up in the range of a few megahertz. And so 10 kilohertz just can't get through. Right. But it can couple into a different mode. It's a plasma wave. Because it sounds like these whistling tones, that was called the Whistler mode. And the interesting thing about the Whistler mode is that these radio waves no longer propagate in straight lines, but they tend to follow the magnetic field line of the planet.
Right.
And furthermore, the higher frequency waves can travel faster than the lower frequency waves. So what starts out as basically an instantaneous burst of electromagnetic energy, at least in the frequency range from a few kilohertz up to 10 kilohertz or more, turns into a whistling tone where you hear the high frequencies first, followed by the lower frequencies. So it kind of goes.
I think we can hear that now because I think you have a recording from the Earth thunderstorms, don't you?
Right. Let me play that. And I have to say that this is from an instrument that we flew on a mission called Van Allen probes to study Earth's radiation belts.
Right. Right, yeah.
That's a very high quality receiver. It has many more than 4 bits resolution. We have multiple sensors, so that's the way you'd like to make this measurement. Unfortunately, Voyager wasn't that advanced. It was built in the early to mid 1970s. But when we flew past Jupiter, we detected these sounds.
Well, that sounds very much like the Earth sound, doesn't it?
Right. They're not very clear. You might say that, well, that's just because it's a 4-bit measurement. I think that's not actually the reason why they're hard to hear. The reason why they're hard to hear is, in addition to this whistling tone, there's a lot of, you would call it white noise or hiss, like tape hiss, that doesn't come from an instrument, but it comes from the equivalent of, it comes from Jupiter's magnetosphere. There's this giant torus of very dense plasma that comes from the volcanic emissions from the moon Io. And there are all sorts of plasma waves that propagate in that plasma. And so we can hear the whistlers when that noise has kind of dropped in amplitude. So it's basically a competition between the whistling tones we're trying to hear and other naturally occurring waves in that region of Jupiter's environment. So the low frequency rumbling or hiss that you hear there is actually a natural signal from Jupiter also, but it kind of masks what we're trying to hear. So the interesting thing is when we detected these signals, we didn't actually listen to them at first. We displayed them on what we call a frequency time spectrogram. If you've ever seen a voice print, or there's lots of apps now that allow you to listen to birds, and they show a display that shows frequency and time and amplitude. We look at displays like that for most of our scientific work. And we saw these whistling tones show up, and we thought, boy, that sure looks like a lightning whistler. And we actually took these 4-bit measurements and ran them through a digital to analog converter and then through an amplifier so that we could listen to them. And it was basically after we had done that we convinced ourselves that, yes, those are lightning whistlers. And so at that point in time, we didn't know lightning existed at any other planet other than Earth.
Right.
So this was the first detection of non-terrestrial lightning. the people on the imaging team with the cameras had turned Voyager's cameras back to take pictures of the night side, and they took basically time exposures, not terribly long ones, and they noticed that there were splotches of bright areas in the atmosphere and deduced that those must be clouds that are lit from beneath by lightning strokes. These two papers came out simultaneously. Officially, you would say it was a joint detection, but we think we had figured this out before the imaging team had.
Yeah, and they basically confirmed your findings then in the end.
Yeah.
I mean, the lightning itself, which is really quite fascinating. As you said, it's the first time lightning's been observed in the flesh, so to speak, outside Earth. But it's not the only sound. I think we also get when the solar wind, particles ejected from the sun, hit the magnetosphere, don't we?
So the solar wind is a gas that I like to say it boils off the sun, and it gets accelerated by processes that we're only now beginning to understand with missions like Parker Solar Probe and Solar Orbiter. But these particles get accelerated to speeds of like 1,000,000 miles per hour, and they move out radially from the sun. They pass all the planets at this very high speed. And when they hit an obstacle, and in the case of Earth and Jupiter that have magnetic fields, the magnetic field sets up as a bubble, basically, in the solar wind. So the solar wind is moving past that bubble at supersonic speeds. Even though it's a charged gas, it's got electrons and ions and so on, it's not dissimilar from a sonic boom that one might hear when a supersonic jet flies over.
Right.
Basically, the jet is flying faster than the speed of sound in the atmosphere, and the solar wind is moving past the planets at supersonic speeds in the same way. And so what happens upstream of these magnetic bubbles, there's a shock. We call it a bow shock.
Right.
But in many respects, it's very similar to a sonic boom, only it takes place in space as opposed to our atmosphere. So we have a very nice recording that Voyager made as it approached Jupiter. It crossed this bow shock. We have many of these crossings from Voyager and Galileo and other spacecraft, but this one's particularly nice. And in the recording I'm going to play, at first you'll hear some very high-pitched squeaks. And those are what we call electron plasma oscillations. They're a very simple mode in a plasma where the electrons kind of slosh back and forth.
Yeah.
And there's a particular frequency that they do that at that's determined by the mass of the electrons and the number density. That is, how many electrons per unit volume there are. And this is important because later we'll listen to some more of these plasma oscillations in the interstellar medium, but it also is a very neat way of understanding the density of plasma in space. It's not a very easy measurement to make. You would think you would send a plasma device out there and just count particles. But that's easier said than done because the spacecraft tends to charge up and a lot of the electrons that we're trying to measure get repelled from the spacecraft if it's charged. And so it's not an easy measurement to make, but the fact that we can detect these plasma oscillations, they basically are formed by the plasma that extends a distance from the spacecraft, and they're less perturbed by the spacecraft itself. So I'm going to play this recording. First, we'll hear the plasma oscillations in the solar wind before we get to the shock, and you'll have no doubt picking out the shock when we go through it. Okay, so I like to think that I'm standing on a beach and a great big wave comes up towards the shore and breaks over me. I think that's exactly what this reminds me of.
And it sounds quite eerie. I mean, you have to remember that's, from a different planet. And You also indicated that we get these kind of plasma oscillations also in interstellar space, which is where Voyager is right now.
Right.
And you also have a sound sample there. So what does it sound like? And why is it interesting to actually look at these plasma oscillations or different densities in interstellar space?
They represent the first time we've actually stepped foot beyond the sun's atmosphere. The sun's atmosphere is basically, we call it the heliosphere. It's a region in space that's dominated by plasma from the sun and magnetic fields from the sun. And then there's a boundary between the heliosphere and the interstellar medium, the stuff between the stars, which we call the heliopause. And Voyager crossed that boundary Voyager 1 crossed it back in 2012. And so we've been traveling outward from that for many years now. There is a plasma instrument on Voyager 2, but it didn't cross this boundary until 2018. So Voyager 1 was traveling through this medium. We were measuring galactic cosmic rays. We were measuring magnetic fields, energetic particles, and we were measuring plasma waves. And we detected a couple of events called plasma oscillations.
Right.
And by using the frequency of those plasma oscillations, we could say, oh, we know what the density of electrons is, meaning we know what the plasma density is in the interstellar medium. And what's interesting is that as time went on, the frequency of those emissions continued to go up from a low of about 2 kilohertz up to 3.5 kilohertz or so. So that's telling us that as the spacecraft moves outward from this heliopause, there's a gradient in the plasma density. That is, the density increases as you go farther out, which, at least in my mind, sounds a little bit counterintuitive.
Yeah.
And
I would have thought the other way around, actually.
Yeah, and we're still trying to understand that. The people who do the theory and do simulations, they say, oh, this is exactly what you'd expect. Well,
okay. Good on them.
So anyway, we can listen to those. This is kind of a swindle. We can talk more about how we get data back from Voyager from the interstellar medium, but we don't get very much at all. Basically, we get a measurement one or a few times per week for less than a minute. And so we've kind of compressed all this data together, and we've tried to keep the frequency exactly as it was detected by Voyager. And so I'm going to play this, and you'll hear two events. And the first one is at a somewhat lower frequency than the second event. And this takes place over about 6 months, a little bit more than 6 months.
Okay.
So
you get a whistle. It sounds like a whistle.
It's a whistle, yeah. Actually, it's in most cases, it's a fairly pure tone. We've detected that there are some multiple frequencies involved, but they're all fairly close to the primary frequency. There's some plasma physics associated with that we're looking at, but to first order, the frequency of those emissions is telling us, the first event was somewhat lower frequency, the second event was somewhat higher frequency. That says that Voyager is moving through an increasing plasma density. Since then, we've measured another 5 or 6 events like this. And even more recently, the spacecraft have detected a very weak, thin line at this plasma frequency we haven't seen the plasma oscillation since about 2019.
Right.
But we're seeing this very thin line that's enabling us to continue to track the density in the interstellar medium. And it's kind of leveled off. If we were to detect plasma oscillations currently where Voyager 1 is, they'd be at a frequency of about 3.5 kilohertz, which is a little bit higher than the ones we just heard.
I think we have to pause for a second and let this sink in, that we're actually hearing from something from out of the solar system in the interstellar space, which is where no one's gone before.
That's right. I should say that astronomers try to deduce the interstellar environment, but that by looking at starlight from stars, and they look at the spectrum and various aspects of the emissions from the stars, and they had concluded that the plasma density around the sun's heliosphere in the interstellar medium was about the same frequency, about the same density that we're measuring. So you could say that this isn't a big surprise, but it is the first time we actually went out and stuck our toe in the ocean and figured out what was there.
Yeah, indeed. Yeah, no, I find it absolutely fascinating and breathtaking. And it's still going. So how long do you think Voyager is running for? In the sense, it's running, until it's whatever happens in space. But how long will it be able to send data, I think is the question.
Well, there's two questions there, and I'm going to answer the one you didn't ask first. And that is, both of the Voyagers are no longer in orbit around the sun. They're orbiting the galaxy.
Okay.
And the chances of them running into anything are exceedingly tiny. They'll probably last for billions of years. And in fact, it's possible the sun will go red giant in 5 or 10 billion years. Earth will no longer be here. And these two spacecraft will be relics of an ancient civilization that lived on a planet that no longer exists. Hopefully, that civilization will figure out how to extend itself beyond the Earth when astrophysics takes over. But it's really daunting to think about sending these artifacts out into the galaxy to possibly exist longer than Earth.
Indeed.
Okay, so they certainly won't be sending back data for billions of years.
No, I wouldn't think so.
I like to think of them as my elderly grandparents or elderly parents. When you get to be a certain age, there's all sorts of things that can go wrong in the human body, and just about any one of them can spell disaster. So on the Voyagers, there's a number of issues that we have to worry about. They're driven by basically the radioactive decay of plutonium-238.
Right.
And that has a half-life of 88 years. The Voyagers have been flying for almost 48 years now. So that tells you that the amount of energy, the amount of heat that radioactive decay can put out has dropped considerably.
Yes.
Basically, what happens is that heat is used with thermocouples that convert the heat into electricity. And when Voyager was launched, they had a capability of something like 450 watts. And currently they're down somewhat above a couple of hundred watts capability. I don't know
Less
the
than
exact
half.
numbers. And they're losing about 4 watts per year. And so over the past several years, the engineers at the Jet Propulsion Lab have started turning parts of the spacecraft off that are no longer needed. For example, they turned the cameras off shortly after taking this pale blue dot picture that many of you have seen. That was courtesy of Carl Sagan. He said, we really have to turn around and look at the solar system before we turn off the cameras. And so we did that. But then we turned the cameras off. We turned off basically all but 4 or 5 of the instruments. And the 4 or 5 instruments that were left were the magnetometer, the plasma wave instrument, 2 or 3 particle instruments, those that could best tell us about the outer heliosphere and now the interstellar medium. Recently, they've been turning off some of those particle instruments because they take on the order of 4 or 5 watts.
Right.
And so if you turn one of those off, you buy another year or so of lifetime from the power source. They've turned off heaters. They've turned off redundant systems that aren't needed. And so they're basically managing the power by turning things off. And we now have basically 3 science instruments that are on both spacecraft. And probably in another year, another one of those instruments will have to be turned off. We don't know, but that's kind of the plan. The other aspect with decreasing power is the spacecraft are getting colder. The spacecraft are basically heated by the energy that's dissipated in the electrical systems, excess power from the plutonium, things like that. as there's less and less power being used by the spacecraft systems, there's less heat being generated by those systems. And there's concern that we might freeze the hydrazine that go out to some of these thrusters. We've talked a little bit about the possibility of these thrusters getting clogged. So there's all sorts of things that can go wrong with the spacecraft that could end the mission, just like your elderly parent could come down with some disease or a fall or something like that, and that spells disaster in the end.
But, for the time being, it's still running and it's still sending data, which is what I want to get back to, or what I want to get to next. The collection of the data, because, it's now almost a light day away. One of them, at least. I think the other one is 18 hours away or something like that. I looked it up recently.
Right.
Or 19 hours. So how do you get the data back? And how do you actually capture the data and send commands? How is this process working?
The way this was originally designed to work and has been working for almost 48 years now. By the way, we're really hoping that we can get the spacecraft to the 50-year mark.
I hope so too, or beyond.
Or beyond, of course. There are 3 complexes situated around the globe that we call this Deep Space Network. And there's a complex at Goldstone, California. There's one in Madrid, Spain, and there's one near Canberra, Australia. And so they're kind of situated roughly 120 degrees in longitude around the Earth. The amount of energy that they collect from Voyager, and this is an old number, it's probably much less, is about a 20 billionth of the amount of power that runs my digital watch.
All right.
And the way they do this is they use a very large collecting area. Originally, the Voyagers could send back 115,000 bits per second, 115 kilobits per second from Jupiter. And they would be tracked by dishes at the Deep Space Network. They have 70-meter dishes at each of these 3 complexes, one each. And currently they have a number of other 34-meter dishes, which are smaller, and they're used primarily for spacecraft. They're not as far as the Voyagers are. The nominal data rate from each of the Voyagers right now is 160 bits per second. And,
considerably less.
Included in those 160 bits are all the engineering information that we get back from the spacecraft, and a few tens of bits per second from each of the remaining instruments.
Wow.
So the plasma wave instrument in particular, we get about 10 bits per second. We get a very crude spectrum once every 16 seconds, I believe. It basically tells us what the amplitude is in 16 different spectral channels from 10 hertz to 56 kilohertz. Those data come down in real time from the spacecraft continuously. But the Deep Space Network has lots of other missions to track. And
Indeed.
Voyager is only tracked, either of the Voyagers is only tracked several hours per day. I think the average is around 8 hours per day. Some days we get very little data. Other days we might get 16 hours or something like that. So if the Deep Space Network is not tracking Voyager, we have a gap in that data. Now, the data that we've been listening to is recorded on the spacecraft at 115 kilobits per second. So we could get that in real time from Jupiter. But after Jupiter, if we wanted any of those data at all, we had to record them on the spacecraft tape recorder.
Yeah.
This is a digital tape recorder. So they would get recorded at 115 kilobits per second. And recently, we've been doing that about once per week for 48 seconds. They get recorded on the tape recorder on board. And after 6 months, we've basically filled up about half of the digital tape recorder capacity. And then they play that back. It takes several hour, maybe 6 to 8 hour, probably about 8 hour track from like the Madrid station. But in order to get the maximum data that we can get from Voyager now is about 1.4 kilobits. So we've dropped from 115 kilobits down to 1.4 kilobits. And to get that, It takes one 70-meter dish and four 34-meter dishes, all tracking Voyager simultaneously.
For hours.
And that's barely enough to get a reasonable signal to noise so that we can detect our data within that data stream. Now, the other part of the problem is that the slowest playback speed of the digital tape recorder is not 1.4 kilobits, it's 7.2 kilobit. What that means is we can't get all the data back. The tape recorder plays back at 7.2 kilobits per second. I mentioned earlier that we record our data on a imaging line. We get 1,600 4-bit samples for each line. And so when one of those lines comes off the tape recorder, it goes to the telemetry buffer, which spews it out at like 1.4 kilobits per second. Meanwhile, the next 4 lines come off the tape recorder and basically go into the bit bucket.
Right.
They get lost. And then the next line, the 6th line comes off, and that gets transmitted to the ground. So out of these 800 snapshots of our waveform data, we get about a fifth of those.
This is obviously something that people find probably difficult to imagine. I certainly find it difficult to imagine because, after all, in addition to the signal loss that you get over this huge distance and the energy loss of the craft itself, it's also the fact that we're talking about a different generation of technology, aren't we?
Yes.
This was designed in the 70s. I mean, it was launched in 77, but it means it relies on technology of before then, because you don't build something like that in a day.
The early 70s at the most recent.
Exactly. And it's a question of data preservation in my mind. Sort of, you collect all the data with technology that was basically designed at the beginning of the 70s. How can you still deal with the data half a century later when technology moved on really massively?
Well, that's a very complex question, and there are many aspects to that. I should say that the Deep Space Network has been upgraded. I think when Voyager originally launched, the 70-meter dishes were only 64 meters. They've all been made bigger. This was partly to get a higher data rate back from Saturn, Uranus, and Neptune. They've enlisted VLA during the Neptune flyby to increase the amount of data that they could return. The format of the data themselves has remained basically fixed. It's hard to do much on a spacecraft that's a light day away. When we launched, I think the data were processed on it might have been an IBM computer. I'm not absolutely sure about that. And the data originally existed on 9-track digital tapes on the ground. At the University of Iowa, we had a UNIVAC machine that used 7-track tapes. So they had to write 7-track magnetic tapes, big reels of tapes.
Right. Yeah,
and
I remember those.
ship them to us with this data on, and then we would read the tapes on our computers. And it's interesting, when we first got the data from the bow shock at Jupiter, we would process each 48-second frame individually, and it would take a half an hour to do the Fourier transform to spectrum analyze those waveforms for one 48-second frame. Another part of the story is how we ended up getting so much data from Jupiter. I won't go into that, but we ended up getting a pallet of tapes on our loading dock one day that had all this data from Jupiter that I think there were thousands of these 48-second frames in that pallet of tapes. And, it took a half an hour per frame to do the processing. Now we can go through all that almost instantaneously. It takes very little time. I remember we had to buy a hard disk for our UNIVAC machine for Voyager, which I think it had 20 megabytes of storage. Now,
it's unimaginable today, isn't it?
Thousands of times more than that. That's
yes, indeed.
But this was a big beast, and it cost about $20,000, as I recall.
So going back to the recordings, so I mentioned earlier that I came across it through a recording, which is actually on sale, and I bought the CD for my sins. But I was wondering, when I listened to that sounds a very slick sound, and, it runs for 30 minutes. They call it the Symphony of the Planets, but each planet gets 30 minutes. But what we're talking about is actually we only get a few seconds, 48 seconds. I think there's a bit of a story of how these recordings came about, at least at the beginning of it.
I know part of the story, and I think there's pieces in the middle that I don't know. and I'll try to be as truthful as I can. The original principal investigator for the Voyager investigation, the PWS as we call it, was Fred Scarf, and he worked at the TRW company in Redondo Beach, California. He actually used these recordings that we've been listening to in press briefings during the planetary flybys. You know, we didn't have the web, we didn't have the internet. Basically, the news got out. The press corps would show up at the Jet Propulsion Lab for like 2 weeks around each of these flybys. And every day there would be a press briefing, and the imaging team would show their latest and greatest images, which attracted all the attention. Fred Scarf, on the other hand, thought, well, you know, we can make sounds out of these measurements we're making, and people can relate to sound more than a wiggly line on a graph.
Indeed.
And so he would play, I don't know how many times he did this, probably a half dozen for Jupiter. The press really got into it, especially the radio stations. Here was something that they could play from Voyager that their listeners could listen to. They didn't need pictures or anything like that. So it was a great tool to relate the type of science that we were doing to the general public. And so we started doing that. And basically, we had kind of a jury-rigged system. We had a special piece of hardware hooked to our UNIVAC computer that would take the digital data from these 7-track tapes and run them through a digital to analog converter and into an amplifier. And then we would record that on a cassette tape. You remember cassette tapes?
Oh, yeah, I do.
So I've got a collection of cassette tapes, and we would send a copy to Fred Scarf. And somewhere along the line, he was approached by someone from a company that at the time was called Brain Mind Research.
That sounds ominous.
Well, and actually, I have a web page that I can send you that actually mentions brain mind research. And it traces the history of the Symphony of the Planets back to Voyager. And so this is the company to which Fred Scarf gave some of these short recordings of the Voyager observations. Several months after he did that, I got a set of 4 cassette tapes from this company, Brain Mind Research. I thought, oh, wonder what this is. And I put one in the tape player and started playing it. And I thought, I don't understand what this is. And the part I don't really know is what they did to create these tapes. But as you have pointed out, they're not short snippets. They're very long. They last a half an hour or whatever.
Yeah.
So somehow they have slowed the data rate down. They've stretched it out. I think the frequencies have been retained, probably not as high as they were originally. So there's some kind of sound processing that took place that I'm not privy to. I don't understand how they did it. But the original set of cassette tapes was marketed as relaxation tapes.
And they are. I can testify to that. It still works for me.
Yep. You fall asleep within the first 15 minutes. Right?
I go in a kind of trance-like state. Yeah.
So these are marketed now as a Symphony of the Planets. I think if you Google that, you can find a number of different sources for these. I think you can buy them. You might be able to listen to them online for free. I don't know.
But what I would like to listen to at the end of our interview, which we now reached, I think there's another sample that you have, isn't it? So we have played almost all the samples, but I think there was one left.
Was it the radiation belts at Uranus, maybe?
I think it was, yes.
Okay. This has a nice story because it ended up in a kind of a cheesy sci-fi movie.
Oh, did it? Which one?
Yes. It was called The Arrival, and Charlie Sheen was the star of that.
The young Charlie Sheen at the time.
Yeah, here it is.
Yeah, you can imagine that it's in a cheesy sci-fi film.
Yeah, well, basically what happened here, those emissions we identified as Whistler mode chorus. So the Whistler mode means that these waves are propagating the same way those lightning waves propagate in the ionosphere. Chorus means that when they were first detected at Earth, somebody in the UK, I believe, said, oh, that sounds like dawn chorus. And in the UK, that means a flock of birds off in the distance chirping in the morning. When we detect these at Earth, they're short rising tone frequencies. Probably have some of those I could play for you if you want. But they're basically plasma waves that interact with energetic electrons in Uranus's magnetosphere. And this is a very important mechanism in Earth's radiation belts that accelerates electrons to very high energies.
Right.
This is something that the Van Allen probes studied in detail to explain the radiation belts at Earth. So we managed to catch some of these as we flew by Uranus, and it turned out that they're probably some of the more intense chorus emissions that we've ever detected in the solar system. There are some that are more intense at Earth, but they're pretty rare. Since I found this, I'm going to play this Earth recording of chorus here just briefly. So those are much more musical than the ones at Uranus, but we think they're the same type of beast.
I can't thank you enough, Bill. This was a pleasure to talk to you today. And all the best for the future and all the best to Voyager. I'm trying to resist not to mention that Star Trek line of saying live long and prosper, but sort of it feels kind of appropriate in that circumstance.
Okay with me.
Okay, thank you. Well, we've been talking so much about the symphonies of the planets, and I thought that it might be a good idea to give you a little snippet and a little idea what it actually sounds like. And all of that is publicly available, by the way. The following snippet is called The Rings of Uranus. Well, it's a bit eerie, isn't it? And you need a bit of imagination to trace it back to the actual recordings from Voyager, the ones that you've just heard earlier. But as I said during the interview, in terms of relaxing and relaxation, it really works. If you want to find out what the Voyager probes are up to, you can do that directly from the NASA websites, which are included in the show notes, of course. Next week, we're going to return firmly to planet Earth with my guest Phil Reed, a fellow of the Software Sustainability Institute and a research community and training manager at the eScience Lab at the University of Manchester in the UK. And I hope you tune in then. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.